Okay, Brian. Like what? This is some.
Recording started.
Okay.
Hello, am I audible? Yeah. Okay. So, have you guys gone through the week's content? Is there anything specific that I should revise back? Or if you guys have any doubts?
आंटी ने सुबह ऑलरेडी कर लिया। आंटी ने सुबह ऑलरेडी कर लिया। आंटी ओनर
Hello?
Sir, can you explain the bias and variance concept? Like, suppose we have the bias, high bias, then what should be added? Like, I did it like I was knowing that we need to add the regularization,
Mm-hmm.
but it's not the answer. So, can you please explain how it is?
Okay. So, you want some bias and variance trade off.
Yeah, like what happens when there is high bias and what effects to the model and
Okay. So, this is one. If anyone has any other points, we'll just list them down and then start going over them one by one.
yeah, sir. One more question.
Mm-hmm.
It's of week 6 assignment. In that padding and stride was one question.
Okay.
I didn't got that question how it is solved.
Uh, can you tell me what was in the content of that question?
Yeah, it was the input feature map was of 7 cross 7.
Okay.
Then the spatial resolution we need is 14 cross 14 for the transpose convolutional operation, and we have the kernel size 3 cross 3. So what stride and padding must we add to get it? This option was stride 2 and no padding, then stride 1 with padding 1, stride 2 padding 1, and stride 3 no padding.
Okay, so stride and padding is to be estimated.
Yeah.
Okay. Okay. Any more questions? Like,
If you want, I can place it in chat box.
yeah, I mean, the details that I have written, they are full, right?
Okay, no, yeah, okay, okay.
I mean, can you confirm once? Like, the input feature map was 7 cross 7.
Yeah, it's correct, it's
Okay.
correct.
Okay.
It's this convolutional transpose
Yeah.
operation.
Yeah. You want transposing operations.
Yeah, yeah.
Okay. Any other questions? Maybe I will first cover this second question actually, because that is slightly smaller. So, uh, you remember the formula that was used when we were doing the normal convolution operation? So, if I want to find
Yeah.
out the output feature map size, and I have certain padding, some stride, some padding, and some kernel size, and my input is, let's say, size n cross n. So, do you remember the formula that was being used?
Yeah, it was input minus kernel plus 2 padding
Mm-hmm.
divided by S the stride plus 1.
Yeah. So now what we are looking at is, so this operation that we were doing, the normal convolution operation, that was actually reducing the feature map size. So you started from some n, and that was getting reduced to some o, right? So with transpose convolution, we are actually looking at the exact, I mean, opposite of this thing. We have some input map which is of smaller size, and we want to kind of expand it and make it bigger. Okay, so you can essentially use this same formula to just revert the process. So if I if I write n in terms of o now using that formula, it will look something like firstly o minus 1 into s plus k minus 2p is equal to n, right? Is that making sense?
Yes.
Yeah. So now this n is so if I had an input map of feature size n, I would have gotten the output map of some feature size by this formula. But we now are doing the exact opposite operation. So you send in an input map of, let's say, in this particular example, the size was 7 cross 7. So O is now your input. Okay. So you put 7 minus 1. The stride is something we don't know, so we are keeping it as S right now. Kernel size has been given to us as 3, and we want to find the padding also. and we know the output size, which is supposed to be 14. So we can actually do 6s plus 3 minus 2p is actually here 14 minus 3 11. Oh, I should have put that. Okay. Am I making some mistake here? What were the options for this thing? I think I made some mistake here.
It's stride 2 and no padding, then stride 1 with 1 padding, then stride 2 with padding 1, and stride 3 with no padding.
Was there any correction for this question?
I don't know about it. I guess no.
In the discussion forums, there was nothing specified.
No, no. I shared the question in the chat box for the options.
Yeah, everything seems right. Okay, I think I'll check back at the first option works. Huh?
Yes, the answer is that one.
Kernel size 2 cross 2. Was there any correction given in the question that the kernel is supposed to be 2?
Yeah, it was discussed in the that forum.
Okay.
People have raised it. So the response was that the kernel size should be 2 cross 2.
Okay. So I mean that's your answer. So
Okay.
if you put this as 2, so that would have given us a 12 here, and then the 2 2
Okay,
and
same.
then
Yeah. Hmm.
so stride 2 0 padding works here. Okay. But yeah, that is the general process. So
Yeah, but I remember the process record. It's good.
okay, no problem.
Thank you. Thank you.
Then we have one more. So this is resolved. We need some info on bias versus variance trade-off. Okay. Actually, during okay, I will try to search a code I had shown some during one of the previous weeks. Give me a few minutes.
Hello, sir. Is it the 10th week questions or previous questions?
No, I'm just answering some doubt questions that were raised.
Yeah. Okay. Okay. Good, sir. Good.
Yeah, just give me a few minutes. I will find that code. Okay. So before we jump to the code, I think I will do some primer. So mainly the question is about what happens when the bias is high, what happens when the variance is high, and is that the question?
Yes.
So
Yes.
maybe we'll take some dummy data. So or maybe okay, just for the sake of this example, let's say you have some feature x1 which is determining your output y, okay, and let's say the data is of some sort of some function like this. So as you can see here, the x1 feature is actually the way the mapping works. So this let's say a function, underlying function from x1 to where y, uh, in reality we don't know what this underlying function is. So let's say we are approximating it with some function, so you get some prediction of y, and let's say you chose for this kind of data, for example you chose a linear model, so in which case the prediction of this input x1, you are going to assume it of some sort like this, right? Is this part okay? Is the context clear?
Yes.
Yeah, okay. So if you assumed a linear function mapping from this x1 feature to your predicted output y hat, so that might, let's say even in the best case you did fit it, it might go something like that. So imagine this as a straight line. So as you can see here, the data I mean, you have not really fit to the data very well. You used a first order polynomial, which is just a line, and you incurred, like, you basically didn't very well map to the entire data. So such a case we actually call, but at any point, let's say now once I did fit a line to this thing, if I did choose a new point, let's say, which is some new feature x value, and I wanted to do the prediction for it, I would put it at this location, and the next output that I'm let's say somewhere around this chosen input, if I had some other data point, its output also is kind of close to it, right? It's not wildly different from my output at the previous location. Is this part making sense? So we talked about two things. One is that the uh, first point is that the lower order polynomial did not fit the data well. Okay, but the second point that we have observed is that the outputs for new inputs, I would say, okay. So this is what this case that we are seeing here, what is that case called? High bias, yes. And also it's a high bias and dash variance. Yeah, exactly.
Yeah.
So that is why I said that the outputs are not wildly varying. So it's a case of high bias. High bias because my model didn't fit to the model had a lot of bias towards what it it predicts. It is not fitting well, or rather the bias in the sense, like just the term exactly you can relate to we having a bias about something. So my model is not conforming well to the data. Prediction is not varying is the variance part. Okay, so this particular example that we just saw, that is a case of high bias but low variance. And instead of this, we'll draw it again. Some this similar data. If I try to fit, let's say, a cubic to this thing, that cubic might look something like that. Okay, so assume that the curve is smooth. Now the cubic is kind of fitting. Is it the test data? No, right now I'm only talking about some training data. The test data is where the variance part came in. Right, we looked at two new data points where the output we looked at, and there we talked about the variance. So this part that I'm fitting to is still the training data. Okay, so now I tried a cubic fit, and that seems to fit the data relatively well. So I would say that my model, the model of f of, let's say, I'm calling this x, the feature x and the output y. So my prediction y hat is relatively less biased than the previous case. So less bias means it has conformed well to the input data that I was using to fit the model itself. Okay, so this is a case with a low bias, and still, even if I take two new test cases, and I check the output of those cases, it's not wildly, still not in the sense, it's not too different. It's not like, uh, I mean, is that part making sense to everyone? That output not wildly varying part. Okay, so that is still I would call a low variance case, and this is actually the case that I am mostly happy with. So my model doesn't have too much of a bias, and it is not having too much of variance also. Uh, we would consider this as doing good. As opposed to this, if I had some data like that, and my model was some very high order polynomial, and it fit right through the entire data. Yeah, we are coming to that.
This is overfit, right?
Yeah, exactly. So in this case, I chose a very high order polynomial. And it turns out that it fit very well to the data. And in this case, I would say my. Can you mute, please? So in this case, my model is having very low bias. So in fact, the model doesn't have any say of its own. It has fit right on the data. So, but in this case, since the polynomial order is very high, I would say that the for any two random test cases that I am looking at, I might get very different outputs, even if they are. Oh, I drew it very. So in reality the function might, so all of this that we are seeing, the data, that might be just some noise, that might not be the part of the underlying process itself. The variance could, the real underlying process might be something like that, or maybe I should. I'll draw it with a different color. So the underlying process might be something like that, which is a not so high varying process. It's relatively smooth process, but my model will end up giving me very different results for the points. So ideally it should have been this thing, but it is predicting me this thing. Will it depend on the power of function? High variance. Yes. I mean, that is one of the things that happen, at least in case of polynomial regression. So as I am increasing the order of the order of the polynomial that I am using for the fitting, I am getting high variance. So this is usually talked about in terms of testing. So I try to take a new point and see what is my model telling me for that point. So in test case, if my error is very high, but my training error was very low, I might say that my model was very well conforming to the training data, but it is varying way too much to the training data, and it's not conforming well on testing case. So in that case, I will say it's a low bias and high variance model, overfitted to training. Exactly. Does that answer your question? Okay. There is actually a. I'll see if I can run this code. Is my screen
Sir,
visible?
can you tell some questions related to this week's assignment?
Yeah, I mean, if you have any doubts, feel free to ask.
I have one doubt, sir. In the previous assignments, one of the questions is the number of parameters, the CNN.
CNN assignment.
Yeah, number of parameters.
Okay.
For example, 34 by 34 into three layers, something like that.
Mm-hmm.
And convolution is like 3 by 3, something like that.
Okay.
How many parameters? And I was wildly wrong.
Oh, okay, okay. Okay, that question. Okay. So you are asking, uh, estimating the number of trainable parameters for a given
Yes,
data.
yes,
Okay.
yes.
So we will come to that. Yeah.
Okay.
Okay. Uh, I'll just cover some of this code and we'll get back to the question. Okay.
Okay, sir. Okay.
So is my code screen visible?
No, no.
I'm sharing a Google Colab notebook. Is that thing not visible? Visible, no? Okay, yeah. So yeah, so I am choosing some example function of this sort, this ax square plus sine of bx, and I need to connect it. Yeah. So here I am actually generating some dummy data using this function, and I'm also adding some uniform noise to the data. Okay. So a and b are these parameters that are defining my underlying function, and the original y is calculated by the function, which is my function, this thing, and I'm adding the noise to it. Okay. So just for the sake of it, I'll run it. So as you can see, the actual the input values that I had put is a was 1 and b was 5. Okay. And so the real curve would have been this blue thing. Okay. But what the data we got, so in general any physical process will not give you like very clean data, so it will have some noise. It might be your measurement noise, and several sources of noise. It could be experimentation error. The procedure itself might not be the best suited procedure for measuring that particular value. Okay. So all of such things that might create some noise in the measurements that you are actually making, and so you ended up getting these red dots as the data points. So we performed polynomial regression on this, and we chose a polynomial of order 2 for this, and you will see, yeah. So this case, the polynomial that we fit was actually, since it's a second order thing, it's a quadratic, and it's a case of high bias and low variance situation. Then we will try to look at what if we fit a 10th order polynomial. Now the high orderness of a polynomial is actually a very relative term. It depends on the data that you are looking at. Here the data itself is having this kind of underlying distribution, and when we did try to fit a 10th order polynomial, it fit very well to the data, right? So it's a case of low bias and low variance situation, and if I try to fit let's some very high order 50, the kind of fit that we have got is actually very much close to the real data points, and also actually printing the errors. So on the training data we are having this kind of error right now for this 50 order polynomial, which is 1.64. Just note that number. And for the 10th order we are getting much higher error, but that is, as we know, it's actually closer to the underlying function. So even if the training error is not necessarily very low, we know that this model, this 10th order fit, was actually more closer to our underlying function. So we would actually go with a low bias and low variance model rather than a low bias and high variance model. Okay, that is actually what I wanted to cover. This was a different. Okay, we will not go through this one. Okay. How do you decide the order? Yeah, I mean, you basically keep running it for. You test different number of features, and yeah, I mean, you basically choose. So when I'm fitting a 50th order polynomial, which means I literally have 50 features. So x square, x cube, all of that till x power 50. How do you get the sweet spot when we can't test all scenarios? I mean, that then depends on your domain knowledge. So let's say for most cases, so in my particular case actually, in my research problem I'm working on some hydrodynamics data, and I'm trying to find a underlying function. So it's my the real dynamics that is actually happening might be of some weird order. I have no idea what order the real underlying process is, but what I do is I choose models only from 3rd, 4th and 5th order, and I just check whether the predictions that I'm getting for different orders are they I mean, I'll just check whether 3rd order is sufficient enough to get me a good match. If it's not, then I will go for 4th order. And for most physical process, if you ask me, somewhere close to 3rd to 5th order, it's very good enough. So it's based on the domain knowledge. Domain knowledge plays a good role in yeah. Okay, so I will jump back to the okay, so there is some question about the estimating the number of trainable parameters for a CNN layer. So okay. You just revisit the what happens when you actually run a CNN model. Okay. Or actually I have some previous okay. Okay, not this. Okay. So this is just a previous sample example. Okay. Let's say you had an input image of size 100 cross 100, and so there are essentially 100 into 100, that many number of features that you have for that particular image, and what CNN operation is actually going to do is it will have this kernel, this that is shown here, kernel, and it will go over the entire data one by one. And I was actually explaining that how similar this is to a moving average or some other sort of kernel. But coming to the main thing, uh, when you are training a model, so when you say kernel, that is actually, let's say you have chosen a 3x3 kernel, so that 3x3 kernel will have 9 numbers, right? When you choose such, so when we were saying that the input channels are so and so and the output channels are so and so, the output channels is actually a number which is telling me how many such 3x3 kernels that I am going to put on my previous channel inputs. Okay, is that part known? Someone asked about this CNN question, right? I hope this is known. Okay, so when I am saying that I have a set of output channels, that essentially means that I have such 3x3 that output channel number of kernels, okay, which I am going to each put on my previous inputs, and I will keep on running that. So yeah, so here I am showing that same example. So my input had only one channel, which was uh, since it was a grayscale image, but my output had 3x3 and such, let's say 50 channels, or maybe I should draw it new. Okay, we'll draw it new. Okay, you had a 100x100 image input and you passed in a 3x3 kernel and such 100 kernels, let's say. So that would result in you putting this across the entire image one by one, and that you are doing essentially 100 times. So whatever is the feature map size of the output, so that feature map size you can calculate based on your stride and uh, padding and whatever those parameters, and so that is your let's say output particular size, and you had 100 such features. So all the numbers that went in here in this 3x3, they are all that you want to train for that layer. Such 3x3, in fact there are 100 such numbers, and along with those, for each of them you actually had, so whatever was the number of so this operation you ran over, let's say since here it's only one input, for each, if this had some different number of channels, let's say C1 number of channels, for each of them you also need to add bias terms. So that goes for the bias part of it. So I should have In fact, per channel for the output, we are having one bias. I actually said it wrong. So this would actually be the number of trainable parameters for this specific layer. Okay. Uh, Whoever asked this question. Is this clear? I guess it is. If anyone has any doubts, feel free to. Am I audible? How suddenly there is no response? Okay. No, if you guys have any more doubts, feel free to ask. I have a doubt related to boosting. Okay.
Can we use any regression or classification model as weak learners in gradient boosting?
Ideally, you can, but in most cases they use those decision trees only. I mean, the process is not very commonly used with other any other models. You can use. I
So,
mean, ideally, it should not have any problem.
so whatever like gradient boosting models which are inbuilt in Python packages, those are only using decision tree models as weak learners.
I'm not
Correct?
really familiar, I think, but they might be. You can Google that, but I'm not really familiar with that.
Okay.
If no doubts from the previous content, we might go over PCA or naive based classifier. Is that okay? Okay. So, principal component analysis. Are you guys familiar with the process, or should I cover some theory of that also?
Yeah, today we listen to the class, sir.
What?
The 10th week PCA is there.
Yeah. So, would you like me to cover some theory, or uh, can we directly go to the
Sir, some assignment questions, sir, please.
assignment?
Assignment related questions.
Okay. Yeah, I mean,
And
the
that may
way.
help because we are only having 3 more weeks, sir. I'm not sure whether I am getting the have, 4 out of 10 also. I'm not really sure about that. So I have to make up these 3 assignments at least to the level of 80%.
Okay. I mean, the thing is, I mean, I believe in that if you have any doubts specific to any questions, I can come up with some close by examples. So we can work
Okay,
through that,
okay, okay,
or
okay.
I will just cover through the theory, and that will give you enough information to
So there is
identify.
there is okay. I think mm, yeah. As you please, sir.
Huh?
Just cover whatever you think that is suitable
Okay,
or
so
right thing for answering the questions.
okay, so I was actually planning to cover some basic theory of PCA, and then I was going to show a code demo, and the same thing I was going to planning to do for naive based classifiers.
Okay.
Okay.
Okay. So basically, Navy base is only for two classes, right?
Yeah, as far as I remember, yeah.
So if you want more than two, you have to go for
No, no,
what is that?
no. Wait. You mean naive based classifier, the application itself?
Yeah,
Yeah, you can apply it to any number of classes. There is no restriction for it to be
but it's
applied to.
binary, na sir. Binary, na?
No, I mean you can. There is a extension of the process that you can apply to get more classification also.
Okay, okay. And today in the class, SVM also covered, sir.
Yeah, but as far as I remember, SVM was not uh, done in very much details.
Yeah. Only 4 minutes video.
Yeah, uh, yeah. I don't
Okay,
remember.
sir. As you please.
Yeah.
Go ahead.
So I'll just go over the basics of what a principal component analysis procedure is about. So principal component analysis is actually a dimensionality reduction technique. Okay. So when we say dimensionality reduction, we are actually more concerned with the cases where, let's say, you collected you have very few samples actually. Your data has fewer samples, but the number of features that you are looking at for each of the data points. So here rows are going to represent the data points, and I'm representing the number of features. I'm putting the features along the columns. So let's say this is the first feature, the second column is denoting the second feature, and so on. So in such a scenario, so you had fewer data but lot more features per data point. This actually causes you to not have a good understanding of how uh, how each feature is affecting that particular data point. Okay, so in general, when you want, this is actually called the curse of dimensionality in ML. If I have too many features, I have some problem understanding what is the effect of each of those features in determining that particular data point. Okay, so uh, why that is the case is essentially the same problem as we saw in case of overfitting. So you had way too many things that you were considering affecting the input, affecting the output, but you had no idea what exactly to choose from that set, which exactly affects or has the maximum impact on your predictions. So in such a case, or in such a case, what you try to do is you try to reduce the dimensions. So if I have, let's say, some 100 features in my for every data point, I might reduce it and try to find, let's say, some 10 features and see how they are affecting my data. So for every data point I will only then look at, so if n data points, I'm now shrink down so from 100 I have tried to shrink it down to 10. So this process of how you can achieve this, but when you do that, you want to do it in such a way that you don't lose information about the real data that you had from those 100 features. You want to lose less information, you want to retain as much as you can. Okay, so that is the goal of PCA. Is that part making sense? So I will just note it down here. Reduce dimensions, but not lose. That is the whole goal, I would say. Not lose too much info. I mean, you are definitely going to lose some information, but you want to minimize that. So we'll have some toy example here. So let's say this has some data and you had some two features x1 and x2. Okay, so this was actually also covered in the lecture notes. So what you essentially try to do is you try to find a new dimension which is perhaps a combination of the previous dimensions that you had, and in this new dimension you will look at what is the if you project all of that data along this new dimension, what is the variance of the data that you are still retaining. So if you had this x1 and x2 as your actual data points, if you try to change it to the principal components, which so principal components are essentially two different directions which are preferably going to be orthogonal. So I'm going to look at two new directions such that the first direction that I'm looking at captures the maximum variability in the data. So if I did project all of these data points onto this line, I will get some new data like that. So this line that we have chosen is actually the line which has if you take the variance of all of this data along this line, that is going to be maximum for this entire data. And so you could have chosen any line in like that or like that, any line, whichever from all the possible lines that you could have chosen. This is actually the line that we choose based on the criteria that you want that line to be along the direction of maximum variance in this input data. Okay, is that part making sense? Okay, and then you look at, since in this direction you captured the maximum variance, and the only direction that other than this that you might be interested in, right, for the 2D case at least, is the direction perpendicular to this. So if I also put a direction perpendicular to this and project all the data onto that direction as well, I will again have a 2D graph, but in this case I will have along the x-axis the PCA1, the first principal component, and in the y direction I will have the other principal component, PCA2. And if I try to now plot all of this data. So for each data point, I'm having for each data point I am having two numbers again. One is denoting its first principal component distance, and the other is denoting its second principal component distance. So in this space the data might look something like this. Okay, so all we have done is we have put a new coordinate axis. One like this and one like this, and we have drawn the diagram here, rotated. Okay, that is what has happened here. This green box and that green box are exactly the same, just rotated. Okay, is that making sense? So now I have a question for you guys. So would you have a third principal component in this case? Perpendicular to screen, but the input data was only in x1 and x2, right? The input data that you tried to do principal component analysis on, that was only in x1 and x2. So there was no x3 component which was actually having. So this data that you are looking at, the white dots that I had drawn before, they are all in this 2D plane only. So if my input space, so we are talking about a orthogonal input space, okay? Yeah, exactly. So these x1 and x2 features are considered independent, and that's why I've drawn them along two perpendicular directions. So if my input space is of dimension n, I can't have more than n principal components. So the entirety of the variance of the input data will get captured in the n principal directions. There can't be any more. Is everyone getting that part? Right. I mean, is it logically making sense to everyone? If you had something in 2D, you can't like produce a third dimension along which it will also have variance. In fact, in this particular case, there is zero variance of the entire data along x3 if there was something along perpendicular to the direction of the screen. We don't have any more information. Exactly. We don't have any information that is telling us that there is so and so variation of the data in that direction along that feature. Okay. So actually the procedure of calculating the PCA was not, I think, discussed in the lectures, but if anyone wants we can cover that, or we will just go to the naive base. Classical. But how many PCA should be chosen for large number of features? Yeah, so that actually depends on how much of the variance of the input data you want to capture. So it will be a value decided by you. So I might say that I want to capture 90% of the variance of all my input data. Then you can choose whatever number of principal components capture till the 90 percent variance, you'll choose that many principal components. Okay. Yeah. So it's going to be a parameter decided by you. Domain knowledge. Yeah, you can say that it's kind of not not necessarily only domain knowledge. It's also a part of like how accurate you want the model. So usually why we do this is what once you have found these 10 features from those 100 features, you are going to apply an ML model that will do some prediction based on these 10 features instead of the previous 100 features. So you might look at the prediction of the ML model based on these 10 features and then decide whether you need more features or not. But are discarding features we think are less important? Yes, I mean the whole idea is that you are taking, it's not discarding features, it's taking a combination of all of these features. So when I drew this line, this is not actually along x1 or x2, it's a combination of x1 and x2. If you try to write a function for it, it will be some function of x1 and x2, right? So ax1 plus bx2 plus c equal to 0. So you are making a combination of the original input features, and you are finding a new weird feature. I mean, it's a combination of previous features, and in that feature you are trying to look at how that feature can be used for your application. But if out say 10 feature 100 features, we choose 10 for which we perform PCA. No, you choose all 100 features and you get out 10 features from using PCA. Is that making sense? So I used the 100 features and I got, okay, didn't get that, okay, fine. So maybe we'll discuss the procedure of PCA. I think that will help with the understanding. So let's say I had some n data points and f features. So I'm purposely drawing it this way just to give the intuition why whatever we are doing, why are we doing that. Okay. So in this case my data points are along the rows and columns are having features, as we previously discussed. So now if I wanted to find the variance of any particular feature, how would I go about doing that? So let's say I want to find the variance of feature, let's say call it f1. Calculate mean of f1 and find variance. Exactly. So I will take the value of whatever the value of feature f1 is along each of the for each of the data points, and I will find the variance of that. So I'll just basically do, let's say f1 of, I'm going to put ith data point minus the mean of all f1s. I'm going to take square of that and divided by the number of data points. Okay, so I'm essentially taking sum of all this. So I got the variance of this f1 feature. Okay, so what PCA is actually doing is it's not looking at only the variance of a particular feature, because if you had only looked at the variance along this direction, you wouldn't have got the idea that it's varying well along in fact it's varying maximum along this direction, right? So what we do is we check the variance of the, in fact the covariance between, let's say, feature f1 and feature f2, let's say. So I will check what is happening when I vary a feature f1, how is the feature f2 varying in my data. In the 2D case, that gives you the covariance essentially, and you do the same procedure. So I will, in multidimensional case, you would have to do it for every other feature. So I will take the look what is the covariance between or variance between the feature f1 and some n f let's say m, some other feature. So I have to do it for all features, okay, and that will give me a covariance matrix which will be of size f cross f, which is the number of features. Is that part making sense? And along the basically the diagonals of this thing, I'm going to put the variance of feature f1. So this thing that we calculated is going to go on the first diagonal element. The second will be the feature variance of feature f2, f3, and so on. And here along the rows, it's going to be the covariance between f1 and f2, f1 and f3, f1 and f4, and so on. Yeah, we get covariance matrix with f cross f number of values. So this is going to give you an information of basically how each feature is related to each other. Okay, I mean not related, how varying one feature affects the other feature. In your example, x1 and x2 are linearly correlated. If x1 and x2 were non-linearly correlated, will PCA help? So in general, even if so PCA won't capture that exactly, so you might need to consider more number of features to really capture that part out. So if I had some data, let's say like that, everything was along this, so the variance that I'm calculating, variance itself is not it's a linear quantity, or yeah, it's not a quantity that will tell me this thing. Okay, is that part making sense? So more number of PCS. Why is this not going? Okay. You are saying more number of principal components might not help. I mean, it's as if the relation between feature f1 and feature f2, they are not they can't be captured with a linear trend. Then there is nothing you can do. It's between f1 and the feature x1 and x2 only. Putting more features will not really help unless those other features are probably derived from x1 and x2, in which case they are not really orthogonal. Then you are looking at the wrong problem, right? So if your features are independent, they are not related to each other, and you are looking at the relation between them. I mean, when I say not related, I mean that x1 is not, let's say, 2x, some x3, that feature that you are talking about, it's not just 2x x1, something like that. In reality, they are all related, and in fact, with this covariance matrix, you are kind of trying to find the how they are varying amongst each other for the data. To answer your question, the adding more number of uh, PCAs might not necessarily help if x1, x2 themselves are at fault. Yeah, it will work excellently for linearly correlated features. And somewhat, if they are not very much, I mean, they are close to linearly related, then also it will do its job. Okay. So coming to the matrix. Yeah, exactly. So coming to the matrix, we have now an F cross F matrix, uh, which was having the variances of each feature with itself, I would say. And the inter feature variance among on the diagonal off diagonal elements. Okay. And since it's a the variance of f1 with f2 is the same as f2 with f1, so this is going to be a symmetric matrix. Okay. So now what we do is we essentially look at the eigenvalues of this matrix. Okay. And we try to basically put these eigenvalues in a order such that the maximum eigenvalue, let's say it's lambda 1, and so you basically put them in descending order, lambda 1, lambda 2, lambda 3, lambda 4, like that. So everyone knows what a eigenvalue really represents, right? Eigenvalue itself, yeah, I mean, in some sense you can say that the it's not necessarily, I mean, can you expand a bit on what you meant when you said transformation? Equivalent to a matrix by which we are multiplying. Okay, I'm not really getting what you are trying to say, but I think you have some good intuition of it. So, just for the sake of getting everyone on page, I will just cover some intuition as to why we are choosing this specific process. Okay. So let's say you had some. So this is actually some extra information. So let's say you had some A matrix, and you are multiplying some x vector with it. So what this matrix is going to do is it's going to essentially rotate that vector x and also scale it. Like value multiplied to a vector doesn't change its direction, but exactly, yeah, okay. So you are right on point. So so let's say you had some matrix A and choose all the possible vectors x that you could multiply this matrix A with and do that multiplication, just imaginary. And for each of those vectors x, what this matrix is going to do is it's going to scale that vector x and possibly rotate it. Okay, but there are some specific special directions in which even if you do this multiplication, this matrix vector multiplication, the vector doesn't change its direction, but it only scales it. Okay, so some special directions. Yeah, exactly. Those are the eigenvectors. And in general, the word eigen itself means special. So there are special directions for this particular matrix. So if you take any vector along those directions, it's only going to get scaled. It's not going to change its direction. And those directions are what you are actually interested in when you are talking about PCS. And the reason that we are aligning, so the scaling factor that we are talked about, that is the eigenvalue. So the vector only scaled, not rotated. Okay, so the scaling that happens for any particular direction is this value lambda, that is determining how much the vector is going to get scaled. So you are essentially trying to find a direction when you arrange it in this order. Let's say highest lambda 1, second highest lambda 2, and so on. You are essentially looking at those directions along which the entire feature is the variation of the entire data along that direction is actually the maximum. The maximum part actually comes from the value being scaled the maximum. Okay, and that essentially gives you the PCA directions. The corresponding eigenvectors of these lambda eigenvalues, they will give you the principal component and directions. Is that making sense? So just a question. So these eigenvectors that we talked about, what will be the dimensionality of these eigenvectors? Yeah, so for each feature we are not exactly each feature. This is the I mean, you can say corresponding to each feature you have one eigenvalue, but whatever is the number of eigenvalues for that particular matrix that you formed here, you are looking at the direction in which this matrix has the maximum eigenvalue, because variance is what you are interested in, right? You started the entire process by finding the direction in which the maximum variance was. So can someone tell me what will be the size or the dimensionality of these eigenvectors? F, exactly. So these, yeah, the eigenvectors themselves are actually an f-dimensional quantity. So to represent this line for me, I'm going to require uh, f number of f numbers basically. So in this case it's going to be 2, because uh, to represent a vector in 2D space you are going to have two components, right? It's going to tell what is the what is its slope basically requires you to know two numbers, y by x. That's the idea. Okay, so the principal component analysis, whenever you are doing, uh, you are actually accompanying the entire thing with these eigenvectors, which are themselves f dimensional, the dimensions of your feature space. And using that, so let's say in reality you, in the best case you would have had, if you had decided to choose all the eigen. So when I said I'm arranging the eigenvalues from maximum to minimum, what I will do is I will essentially check. So this is telling me what percentage of the variance is captured by this particular PCA direction. This lambda 1 is actually telling me that. So if I keep summing this up to a particular lambda, let's say lambda m, and I added up lambda 1 to lambda m divided by that all the lambdas. So summation I equal to 1 to m of all lambdas divided by summation of I equal to 1 to f for all lambdas. I'm looking at this ratio, and at some point this, if that ratio is reaching your desired, let's say 90% mark, then you will say that this has captured 90% of the variance of my data. Is that making sense? So that is how you essentially decide how to get the number of eigenvectors that you need, or rather the number of principal components that you need, and also what those specific principal components should be. Okay, I hope this covers the doubts. Is this part clear to everyone? Yeah. So basically with principal component analysis you didn't discard any particular feature, you rather created new features out of the existing ones, but lesser number of them. I think for the last half an hour we will probably spend on the naive base. So I think the best way to do it is going to be share a problem. So is my code screen visible? Can you give an example when we will use PCA in real life? So there is actually this is actually what my professor used to tell. So he used to work in biological systems. So in that cases they have many different components of the DNA, the gene sequence, and they wanted to basically look at how each of those uh, components are affecting the let's say some other parameter that they were looking at. So in general there are way too many components, and they don't want to train their models using all of those, let's say 10,000 genes. They want to look at only specific let's say some 20 to 30 numbers at max. So that is he used to tell that they would use PCA for that application thoroughly. I mean, I'm not a biology person, so I don't know much in details about it, but you can look at it. Okay, so yeah, this is actually a question I have for you guys. So yeah, uh, so someone asked like whether uh, base classifier can only be used for classifying into two classes. So in this specific example, you can use it for classifying the data into three classes, and we will look at how to do that process. So uh, if possible, I would like you guys to note down these numbers. So you have some input feature x, and y is denoting the class. So the class is only among 1, 2 and 3, and there are some numbers, and your task is actually to find the decision boundaries. So a decision boundary essentially means that at what x value, uh, uh, essentially in this case you will have two decision boundaries. So towards let's say you put all of these x values along a single line. You will choose one particular value of x, which let's say to the left of it you will have one particular class. Between this x value and some other x value you will have the second class, and beyond to the right of the next x value you will have the third class. Okay, so that is what a decision boundary means. And so you are supposed to assume the Gaussian distribution with a variance 1 as the prior, and the means of that you can estimate from the data given. And there is also concept of loss matrix, so I will briefly touch upon that. I hope the loss matrix is visible. So a loss matrix essentially tells you that, as it says here, the Lij indicates the loss for an input x, with I being the true class and j being the predicted class. So along the rows of this matrix are the true class labels, and along the columns are the predicted labels. So what this loss matrix is telling is that if the true class was 1 and I predicted as 1, my loss is going to be 0, which is the correct thing. I mean, you don't want any penalty for predicting the correct answer, right? If your true value was some 1 but you predicted 2, the loss is going to be 1. And if your true value was 1 but you predicted 2, your loss is going to be 2. That is what the numbers in this matrix denote. Okay, is this part making sense to everyone? Feel free to ask if you have any doubts with this question. Confused loss matrix. Yeah, it's like if you are familiar with the confusion matrix concept, it's exactly that, similar to that. Along the rows I'm putting the true class labels, along the columns I'm putting the predicted labels, and the first box is actually telling me if my true label is 0, true label is class 1 and I predict as class 1, what will be the loss. If I predicted the thing correctly, I don't want any loss, right? I mean, I did the correct thing. I should not get any penalty for that. So it's basically telling you what penalty you should incur for the incorrect prediction in each case. Okay. So your task is actually now to design an optimal base classifier, which means you have to find the two x values that will separate out this entire data into class 1, 2 and 3. I'll just give about some 5 to 6 minutes not to solve the question. I think the solving part will take a little longer, but we'll just think about the approach of solving it, and then we'll discuss the solution. I'll keep this part over here, but the loss matrix you might remember, like just 0, 1, 2, 1, 0, 1, 2, 1, 0. So we'll wait till around 7:45 maybe. If you have any questions on how to get started also, I'll give some hints. And my goal is not actually to get into the number crunching here, just the concept of it. maximum number of principal components is less than the number of features. Yeah, I mean that is exactly what we discussed just a while ago, right? In that 2D example case. Is everyone clear with the problem? I hope so. Okay. So we'll start discussing the solution at around 7:45. Do we need to calculate all conditional probabilities? I mean, as I said, I'm not expecting you to solve the entire thing right now. Just, I mean, try to find the procedure or think about the procedure, and uh, maybe then I will open up to you guys to suggest how we can approach this problem, and then we will discuss the solution. Okay. Would anyone like to suggest their approach? Thought about calculating priors and posteriors? Yes, that is exactly what we are going to do. Yeah. What I actually wanted you to think about is how would you incorporate this loss metric concept? what are you trying to maximize or minimize? Okay, yeah, loss, exactly. So this is a classification problem. So ideally, the class that gives you the least cost is the one you want to predict, right? Is that making sense? Okay. So the class that is going to give you, so predicting a particular class. So for any new data point x, if I get, I will predict some y value, right? I can either predict it as class one, I can predict it as class two, or I can predict it as class three. So I will choose the prediction of so for that particular data point x, I will choose that prediction which is resulting in me getting the least loss or least cost by this condition. Is that making sense? No, I am at loss. Okay. Okay. So we will maybe go over the theory part. So our data was looking something like that, like this, right? So yes, okay. Is my screen this thing visible? The tab, what I'm writing? Yeah. Okay. So I had some features x and the actual class labels for all of those features y, and so whatever the values were there for each of the x values. And what we said was that we had to start with a Gaussian distribution with one variance, right? So that was the thing, that was the information that was given to us for the question, right? So let's take a look back at what we are going to achieve when we solve this thing. So here I am putting some cross marks. So let's say these are denoting, so the white ones are denoting class 1. I'll put some green marks, and the green ones are going to denote class 2, and some probably red ones, and the red ones are supposed to denote 3. Okay, maybe the white one I should put yellow. Okay, so now if I am given a new x value, let's say at this point, okay, I want to predict whether it belongs to class 1 or 2 or 3, right? That is essentially what the problem is actually like. Okay, so when I'm predicting, so let's say I have some guess, so we'll so based on this data I can actually make a guess of what should be the mean of class 1. Okay, so all the data points that I have, which are yellow ones, let's say I found that the mean of those is somewhere here, and since I am assuming a Gaussian distribution with unit variance, I can draw a Gaussian distribution something like that. Okay, so I'm saying that I'm assuming around the mean, whatever will be my input x values, I'm more certain for predicting it as class 1, right? And as I go further away, it's going to be less likely to be belonging to class 1, and a Gaussian distribution is actually till infinity, so it has some probability for all the way, but it is probably less. Okay, so maybe I'll draw this also with, and then you have some, let's say you from this data you found that the mean of all the data x values where the actual class prediction was 2, let's say that comes over here, and you mark it with the Gaussian distribution like that, and similarly for class 3. Right, so these are our priors. So these are so we have P of y is equal to 1, the prior, the P of y is equal to 2, and P of y is equal to 3. Yeah, P of C1, C2, C3, they are the priors. Okay, so now I want to, based on this Gaussian distribution and variance 1 assumption, I've actually got these curves, right? So if I wanted to find P of y is equal to C1, given some x value, how would I go about doing that? Conditional probability, yeah. I mean, how would I resolve this P of y equal to C1 given x? P of x1 intersection x, okay, C1 intersection x upon P of x, how do you calculate that value? Yeah, but I mean, okay, the answer that I was actually uh, pointing towards was actually the base rule. So you don't have this information, right? P of y is equal to C1 given some x. So you can find that based on the data that you are given by using. So P of C1, so which is essentially going to be from this data, you will calculate all the class, all the data points for which the class was C1, and you will count them. Let's say there were I don't know how many data points were there, for which we need to predict. Let me cover this. I will. Yeah, data. Yeah, so what you are doing is you are counting the number of ones in this and dividing that by the total uh, number. So that is actually your p of y is equal to 1. I mean the prior. Right. So that can all, I'm just writing this as p of c1. So p of y is equal to 1. I'm writing at p of c1. Okay. So this times p of x given c1 upon the summation of all the p of ci's given x given ci, and I will go from 1 to 3 in this case. Okay. Yeah, so that is the entire thing. So you essentially, for a new x, any random, this blue colored x that you pointed out, we pointed, for this, what is the probability that it belongs to the class C1 we obtained using this expression, right? So now we'll do the same thing and find the probability that this particular x belongs to class C2 and the probability that this particular x belongs to class C3. So you can similarly find out p of y equal to C2 given x and p of y is equal to C3 given x. So for the simplicity of notation, I'm going to call this particular quantity as eta 1. This I'm going to call as eta 2, and this I'm calling as eta 3. Okay. So now we have all class conditions exactly. So I know for a new x what is the probability that it belongs to class C1, what it belongs to class C2, and what is the probability that it belongs to class C3. What I do is I make a vector out of this, let's say. Note that for a general x, this is actually a function of x. Right. Is that making sense? Yeah, I mean, so this p of x given C1 is actually from the Gaussian distribution, right? You have the equation for this thing. Yeah, you have a graph. Yeah, exactly. P of x given C1 is essentially the mean of, so it's going to be 1 upon 2 by 1, since the variance is taken to be 1. I'm not putting the 1 here, or maybe I'll put it here. And exponential of minus of x minus the mean of class 1 upon 2. So this is actually your p of x given C1, right? Yeah. So if you plug in for all the classes here, it's going to be a function of x. Is that making sense? Got it? Yeah. So now what we are doing is I have a function, so any random x that will be sent as input to me, what is the probability of it belonging to class 1, class 2 and class 3. I will multiply this thing with my loss matrix, and I will essentially, so when I multiply this with this row, what is along the column of this? Along the column was the prediction equal to 1 scenario, right? Along the rows I was having the true labels for the loss matrix. So loss matrix was 0, 1, 2, 1, 0, 1, 2, 0, 2, 1, 0. Okay, so if I multiply this vector with this column, I will essentially get 0 times eta 1 plus 1 times eta 2 plus 2 times eta 3. Right, this is what I am actually calling the risk of predicting x as class 1. Is that making sense? The column is for prediction equal to class 1. So that is what I have written here. The column is denoting what happens or what is my loss when my prediction is class 1. So if the real class is 1 and my prediction is 1, this is my loss, right? And if the real class is 2 but my prediction is 1, this is my loss, 1, and so on. So this 2 is real class 3 but my prediction is 1. So based on this I can calculate the risk or the total cost I will incur if I predict the x thing as a class belonging to class 1. Is that making sense? Row wise prediction, column wise real y, exactly. And you do the same thing. So I'm going to call this quantity as R1, and I will similarly calculate R2 and R3, which are essentially this eta vector multiplied with this column and this column. Is that making sense? So now this R1, since eta was actually a function of this eta 1, eta 2, eta 3, they were also a function of x. This R1 is also a function of x, and R2 is also a function of x. R3 is also a function of x, but they are different functions because of this scaling. Is that making sense? Yeah, exactly. So based on this, so all these three functions, I will evaluate it at any known x that I am given. So my test case is some x equal to, let's say, 5, and I'll plug it in this my function R1, R2 and R3, and I will get the values for each of them. Whichever one comes out to be least, that is the one I should predict the class as. That is the whole idea. Okay, so I have the code for the same thing. I'll just quickly show that how those functions actually look like, the risk function and our priors, not the priors, the conditionals. Okay. So I just put the loss matrix here, the same thing, and I've calculated the mean of the data. So the mean of class whenever it is 1, it's coming out to be minus 2.1. Mean of 2 is coming out to be 0.5. I hope my screen is visible. Okay, so mean of class 2, so all the data points belonging to class 2, the mean of that is 0.5, and mean of class 3 is 1.86, and I just did the counting that 5 out of the 14 are belonging to class 1, 4 are for class 2, and so these are our priors, py1, py2 and py3. Okay, and here this eta 1, eta 2, eta 3, they are my posteriors. So as we saw, the same notation I'm using here, right? So this is a function of x, and I'm just plotting that I'm taking some x sample values from -10 to 10,000 of them. This calculation of mean probabilities need to be performed by our code. Yes, exactly. In reality, you can make the code do that. Yeah. Okay. So I'm showing this eta 1, eta 2, eta 3. They turn out to be this kind of functions. So this is without applying our cost matrix. Okay. So here we didn't. These are just the normal posteriors. They had no idea of the risk factor being included. So what this is actually meaning is that wherever the blue line is the maximum, I mean blue line is the topmost line, you can safely predict it as class 1. In this region from this mark to this mark, the orange line is the tallest, I mean the highest among all three, so you can predict it as class 2. And here the green line is at the top, so you can predict it as class 3. Okay, that is what the normal conditional probabilities calculation would tell you. But since we also have this risk factor coming in, so now I am calculating that risk function rx1, rx2 and rx3, and that is also a function of x, as you can see here, and to it goes this etas are going as inputs to it. Okay, and I'm plotting this risk function now. So as you can see here, the risk of predicting an x in this range about till this region, it's the least for class 1. That's why we are going to predict any input x that we get till this point, we are going to predict this as class 1. Is my cursor visible properly? Yeah. So all my inputs up till this point, we can predict them as class 1 because the risk is lowest there. On the right side, it's here, wherever the yellow line is the lowest, you can predict this as class 2, and where the green line is lowest, you can predict it as class 3. This is the risk curve, so you have to look at the lower part of it. Okay, and so if you had a more complicated loss consideration, so let's say it mattered a lot more if you classified a true example of class 1 as let's say class 3, if you had, and you, so a practical example that is popularly given is something like let's say the rows are denoting whether the person has cancer or not, and the columns are denoting your prediction of whether they have cancer or not. So if you predicted, so cancer is there and you predicted as not cancer, that is going to be much dangerous scenario than they don't have cancer and you said that there is cancer, right? So at max they will have to spend more money, but like they won't stop their treatment. Is that making sense? Yeah, so you can implement it with a different cost matrix also. Maybe I will share this code here if anyone wants to take a look at it later. Probably right now it not being sharing. Okay, anyone with link is viewer. Okay, so you can run this thing and check. Okay, so yeah, that's it for today. So we'll conclude the session. Thank you for joining. Okay. Okay. Sure. So I will stop the meeting now.